Okay, so last time, remember, we discussed how to find the solution to the diffusion equation. And so we proved the following theorem, which says, okay, so well, suppose I have a function u of xt, which solves the diffusion equation on the real line. So ut minus some constant k, which is positive, times uxx is equal to 0 on the real line, where x is between minus infinity and infinity, with the initial condition that, well, if I plug in when t is equal to 0, u of x at time 0 is equal to some given function phi of x, right? So this is the initial value problem for the diffusion equation on the real line. Well, then we had the solution formula, which took a while to obtain, which is I can write u of xt as an integral from minus infinity to infinity of a certain special function, which is some kind of exponential with a quadratic term multiplied by a constant that depends on t also. So it turned out being 1 over square root of 4 pi kt, all of this in the square root, and then times this exponential function, e to the minus x minus y squared, where y is the dummy variable you're integrating with respect to, divided by 4kt, and then all this times the initial condition, and you integrate with respect to y. So this is the solution formula for the diffusion equation. Right, and so what does it mean that, right, so just maybe one minor technical point is, well, this is really in the sense that, well, we want to think, what does it mean for this to equal the initial condition when t is equal to 0? Well, notice if I just plug in t equals 0 here, there's a problem because I'm dividing by 0, and so it could be infinite if you just plug in 0, because when you divide by 0, of course, that's infinite if you're not more careful. So what we really mean is that if I take the limit as t goes to 0, t will always be positive, so it's actually the limit as t goes to 0 from the right, but that's not too important. View of xt that this is equal to phi of x, right? And we showed when we derived this formula that this has to be the case, right? So this is one of the key properties we use to actually arrive at the formula, the fact that we wanted the limit to be the initial condition, right? Okay, and so this function that's appearing in the integral that isn't phi is a very special function throughout mathematics. So it's usually called a Gaussian. And in particular, if you have some experience in statistics or probability theory, you've probably encountered this function before. Right, and so for our purposes, we sometimes call this in this case, a specific example of what's called a source function. Right, so I'm going to use the letter S for source. And so the source function for the diffusion equation is this exponential function multiplied by this other factor. So it's 1 over the square root term times e to the minus x squared over 4kt, right? And so notice I can write my integral here as an integral of this source function evaluated at x minus y times phi of y, right? So the solution is given by integral from minus infinity to infinity of source function at x minus y and time t times phi of y dy. So this sometimes helps with like notationally, right? Because this function here is relatively complicated looking, so it helps to like describe it more compactly, just writing it as a source function. As I mentioned a second ago, this is sometimes called a Gaussian, which arises pretty frequently in statistics and probability theory. It's related to these bell curves or normal distributions, which, well, I'm going to draw a picture of the source function in a second. And if you're familiar with these things, you should hopefully make a connection. There's actually a very deep reason why this Gaussian is showing up, which is related to connections with probability theory. but I won't be able to say too much about this because this may be a little bit too advanced for this course. Okay, great. So let's actually just draw a sketch of, well, what is this? What does this source function look like? Just to give some intuition about what's going on with this formula. Right, so well, this will be the graph of the source function, and so this is x, and this is, say, the value of s in the top plot. And so we'll notice that it's going to change depending on which value of t I pick. And in particular, well, let's say we let x equal 0, right? So let's look at the 0 point. We'll notice that, well, what we're going to do is we're going to take t bigger than 0, right? So technically, I guess I should have pointed this out before. Technically, this is defined for t positives, right? Because of this issue we mentioned a second ago, where, well, if you set t equals 0, you're dividing by 0. And so, right, the formula doesn't necessarily make sense. But what you can do is think about values of t that approach 0 from the right? So think about successively smaller and smaller values of t. And so notice that if I look near the origin and t is really small, well, that means that near the origin, since we have this singularity in t, the graph is going to peak, right? So it's going to look something like this. Right, let's say t is small. But as soon as I move away from the origin, as soon as as soon as x is relatively large, well, this exponential term, this e to the minus x squared, will decay pretty quickly, even if t is small, right? I mean, it's going to depend on the rate of the decay is going to depend on which value of t you pick, but eventually it's going to just kind of tail off like this, right? And so on the other hand, if you look at maybe some intermediate t, which is maybe of medium size, well, it's gonna still peak a little bit at the origin, but maybe not so much. So maybe it'll look something like this, which should remind you of a bell curve from statistics or something like that. And on the other hand, if we let t be really large, well, if t is really large, then there's no issue with the singularity at the origin. And so the exponential decay of the exponential factor kind of takes over. And so you're going to get like a very light bump or something like that, right? And so the point is that as t gets smaller and smaller, the source function peaks at the origin, but as t increases, things kind of smooth out and flatten out and become a lot less singular. Right, so the source function peaks. Well, we're looking at it at the point x, right? So we're plugging in peaks when near x equals 0 when t is small, right? Okay, and so the reason I'm mentioning this is, well, what's going on in this integral? So if we look at the solution formula, well, that means that if I plug in x minus y, this should peak when x minus y is 0, right? So it peaks near x minus y equals 0 or x equals y when t is small, right? And so the way to think about this is, well, when t is very small, we should expect this integral to be very close to the function phi of x, which is the initial condition, right? Because this converges as t goes to 0 to phi of x, as we saw above. And so what's going on is, well, the source function, when t is very tiny, it's peaking for values of y that are very close to x, right? Because it's peaking where x is equal to y. And away from this region, it's decaying pretty quickly. And so what the integral does is it basically weights the point x. And as t gets closer and closer to 0, you basically only end up with the value phi of x. And so there's a way that these observations are made more precise using something called the theory of approximate identities, which is something you'll see if you take like a higher level mathematical analysis class, like a higher level real analysis class. These things will show up. But I think it's good to just think about this more intuitively, right? So, right, if I just copy over this graph, and if instead of, right, say instead of this being the point 0, let's say I move the x-axis over, or sorry, I move the point x over, and let's say this is my point x over here, and now I'm looking at values of y, right? So all I've done is just shift the graph over, and so, well, if I shift it over by in this way, it's gonna peak when x minus y is equal to 0, right? Which is the same thing as x equals y, right? Oh, sorry. Sorry. Right, and so again, the main point is that, well, as you let t get closer and closer to 0, well, near my point x, where I'm defining this function, the source function is going to keep increasing, peaking in like a more and more rapidly. And so in this integral, that's going to correspond to basically forcing all of the weight near the point x for phi. And so when you take a limit, you're going to end up just getting the value phi of x, which is sort of one of the reasons why this works. Okay, and so now what I want to talk about is the problem of actually calculating solutions to the diffusion equation, or the initial value problem. And so here you pretty quickly run into some significant issues, unlike with what we saw with the wave equation. And so the main issue is, well, if we go back to this solution formula we have for u of x, it turns out that actually calculating this integral as like a closed form function of x and t, which you can just write down like maybe like sine of something times cosine of something, or a formula like this. This is what we mean when we say closed form. It turns out that this is a very difficult computational task, just because, I mean, integrals involving this Gaussian function are usually very hard to calculate by hand. Right, so the first point is just to notice that calculating the value of u of xt as a closed form function, meaning like if you go back to like one of your earlier calculus classes, like this is just like what would be expected when you were told to calculate an integral, like show it's equal to some function, right? And so actually doing this for the integral involving a Gaussian is very hard in general, right? So there are only a few examples where we can actually calculate by hand. And so what people will typically do if you need to calculate the solution to a solution to the diffusion equation, people will typically use approximation methods, right? These are sometimes called numerical methods. And so in particular, you would typically use a computer to calculate the value of a solution to the diffusion equation, right? You would be given a certain initial condition. There are a variety of computational packages which you can use to very, very closely approximate the value of this integral. And then this would spit out the value of the function at a certain point in space and time. And you would use these computer approximations to get a relatively precise understanding of how the function behaves without actually knowing like what it is as a closed form function. So we're not going to be talking too much about these numerical methods in this class, although they're certainly very important. And if you take future classes in like studying partial differential equations, especially from the applied math perspective or the engineering perspective, you'll encounter a lot of these numerical methods, and you'll hopefully learn them then. But there are still some other ways to understand solutions to this equation. Like we can always, of course, write down a specific integral, and we'll see a few examples of doing this in a minute. And this allows you to use a variety of mathematical tools to understand like the particular qualities of a solution with a given initial condition, even if you maybe don't know exactly what the integral is equal to. And so, well, another common way to think about solutions to the diffusion equation is to use something which is called the error function, which arises in statistics. And so it turns out that we can pretty frequently write solutions to the diffusion equations in terms of this function. And so what I'm going to do is write down what this error function is, and then you'll see why, you'll see the connection pretty quickly. And so it's usually written with like a curly E, RF, ER for error and F for function, and evaluated at the point X. There's some constant which is here for normalization purposes, and then you're integrating from 0 to X, and then you have this Gaussian e to the minus p squared, integrating with respect to p. And so if you go back to our solution formula, well, this solution formula looks a lot like the error function, except it has, the integral has an infinite bound, and there's some things involving t and this function phi. But you can still see the similarities. And so what I'll do now is an example where we can, for a particular choice of initial data, we can write the solution to the diffusion equation in terms of this error function. And so I just want to point out that this is a very important object which arises in statistics, which is related to like normal distributions, which are one of the most important, statistical distributions that arise. If you don't know anything about normal distributions, that's okay, because this is not a probability class. But if you do, then it's worth maybe looking more into this connection, because it turns out to be a pretty deep and interesting connection, which unfortunately I can't say more about here for now. Okay, so let's look at an example though to see why this is the case. And so let's suppose u of xt solves the diffusion equation on the real line. And suppose the initial condition is given by a certain step function. Right, so say the initial condition say phi of x, and let's say phi of x is equal to say 1 if x is between 0 and 1 and 0 otherwise. Right, so if I graph this function, well, here's 0 and here's 1, here's the x-axis, and so the function just looks like this, right? So it's equal to 1 if x is between 0 and 1, including the endpoints, and then it's equal to 0 everywhere else, right? So this is sometimes called like a step function because it looks like a step or something like that. Okay, and so let's plug this into our solution formula. Well, from the theorem, we know that u of xt is equal to 1 over the square root of 4 pi kt times integral from minus infinity to infinity of this Gaussian term, and then times this function evaluated at y. And so now what we want to do is, well, we have to plug in this step formula, the formula for phi, to understand this as a function of x. And so in order to make this a little bit easier, what I'm going to do is I'm going to shift the variables, meaning I'm going to do a substitution. And so I'm going to let w equal x minus y. And I'm going to apply this change of variables. So this means that dw is minus dy, and also y is equal to x minus w, right? And so this means that I can write my solution if I make this substitution. Well, the terms involving the t won't change because I haven't done anything with those. And then, well, I'm replacing x minus y by w, so I just get e to the minus w squared over 4kt. And then I'm replacing y by x minus w, right? So I get phi of x minus w dw. Okay, well, if you're paying attention, you may notice, well, what happened with the minus sign, right? dw is minus dy. Right, so technically there should be a minus sign here, but also notice that since ignoring the x term, right, since I've changed the signs for y and w, there should have been a minus sign here and a plus sign here, right? I should have flipped the signs of the infinities. And so if I switch back to integrating from minus infinity to positive infinity, that will negate the extra minus sign, right? So it ends up just being the integral that I had wrote previously. If you don't believe me, you should just pause the lecture and double check, right? It's a simple calculation which you can do hopefully pretty quickly, and double check that this is indeed what you get when you make the change of variables. And so the reason I did this was, well, now I have, right, so now I've brought the x term into the function phi, so I can now use the definition of phi to simplify this integral, right? And so, well, let's think for a second, what is phi of x minus w equal to? Well, we just have to use the rule that's given to us by the step function definition. And so this should be equal to 1. Now it's equal to 1 not if x is between 0 and 1, but if the input is between 0 and 1, which means x minus w is between 0 and 1, and then it's equal to 0 otherwise. And so what does it mean for x minus w to be between 0 and 1? Well, this means, this means w, well, if I just bring this over, this means x has to be bigger than or equal to w, right? And also that x has to be less than or equal to 1 plus w, right? All I've done was just add w to all parts of the inequality, right? And so what this says is that, well, this function is equal to 1 if x is between w and 1 plus w, and then it's equal to 0 otherwise. And so this will help. This will tell us what the bounds for the integral should become. Right, so now let's continue evaluating this. So I end up with 1 over square root of 4 pi kt. And then I have an integral. Well, I'm only going to be integrating in the region where w is less than or equal to x. So the x should be up here, right? Because remember, w is my variable of integration. And then I also want a lower bound for w. Well, we can read off a lower bound from w from what I just derived up here, right? Because if x is less than or equal to 1 plus w, this implies that w is always bigger than or equal to x minus 1, right? And so this means that this tells me the lower bound should be x minus 1. Right, so upper bound is x, lower bound is x minus 1. And I'm integrating, well, in this region, my function phi is just equal to 1. And then outside this region, it's equal to 0. And so, of course, if I'm just multiplying by 1, let me just not even include that here, right? Okay, and what I want to do now is relate this to the error function we saw above. Well, notice that this function has a 0 on the lower bound and then some term involving x on the upper bound. And also I have this Gaussian with just the dummy variable of integration and no other terms. And so what I have to do is just break up the integral into two pieces and then do a change of variables or a substitution, and I'll be able to write it in terms of this function. And so for the first thing, let me just do a substitution, which turns out to be a common calculation tool for analyzing this type of integral. You'll be doing this type of substitution pretty frequently in order to simplify things. And so what I'll do is I'll let p equal w over the square root of 4k t, right? And so what does this mean? Well, this means that dp is equal to 1 over square root of 4k t dw. And we'll notice I have basically that here in the integral already, except for the 1 over square root of pi term, right? And so if I make this substitution, well, then I end up with integral, the 1 over square root 4kt is going to get absorbed into the dw when I change dw to dp. And so I'm just left with 1 over square root of pi integral of now e to the minus, well, w squared over 4kt is just p squared, right? So I get e to the minus p squared with respect to p. And then I just need to double check, well, what are the bounds? How do the bounds change with respect to this substitution? Right, well, if w is equal to x, then p has to equal x over square root of 4kt, right? So that's the top bound. And then if w is equal to x minus 1, then p is equal to x minus 1 over square root 4kt, right? And so that's the bottom bound. And so now this looks a little bit more like the error function we defined above, right? Except for this factor of 2, which is not so important because you can always renormalize by constants or whatever. And so the only thing we finally have to do is just break up the integral so I have a 0. Right. And so for this to work, we want to make sure that 0 is actually like in between x minus 1 over square root of 4kt and x over square root of 4kt. Or actually, right. So this is just sorry, I'm just getting caught up over like a standard integral manipulation. Well, let's just try to first consider the piece where I have integral from 0 to x over square root 4kt of the Gaussian function, e to the minus p squared dp. Well, the integral I have above is equal to this, but it's equal to this minus the piece corresponding to, let's suppose that x minus 1 is positive, so that the lower bound is bigger than 0. Well, then I just have to subtract off the remaining piece, right? Right, and so the integral in the line above is just equal to the difference of these two integrals. This is just the fact that, okay, well, you can break up the bounds. If you break up the interval that you're integrating over, well, you can separate this up into two pieces in your integral, right? And so maybe I would recommend pausing the lecture for a second and just double checking this calculation. Okay, and then what is this equal to? Well, now I do have like a difference of multiples of this error function. And so in particular, this is now, well, this is equal to 1/2 times the error function evaluated at, well, it's not evaluated at x, it's evaluated at x over square root of 4kt. And then I'm subtracting off 1/2 of this error function which is now evaluated at x minus 1 over square root of 4kt, right? And so this is your solution, right? And so in line with what I mentioned earlier, well, since this function, this ERF function is very commonly used in statistics, there are all sorts of computational packages you can use to very precisely understand the values of this function. And so in practice, what you would do is now go to a computer and plug this in, and the computer would tell you what the function is equal to at a given point with a very high degree of precision. And again, in applied math, this is typically how partial differential equations will be analyzed, because the solution formulas you end up with as soon as you have like a non-trivial PDE become very complicated very quickly, and so you need to use computers to have like a decent computational understanding of what's going on. This, of course, does not mean that the pure math is not important, right? Because how did we find this formula? We didn't find this formula using a computer. We found it by hand using just tools from pure math, right? So, I mean, one of the big things you should take away from this class is that both sides of the theory are important, meaning like the pure mathematical analysis to understand the partial differential equations, and also the computational methods, which we're being exposed to a little bit, but maybe in the future you'll take a more advanced class where you'll understand these computational methods in more detail. Okay. All right, so that's the relation with this error function. I do want to do one more example, which is written out in the textbook in chapter 2.4. So maybe I'll skip some of the details because you can refer to the book. But I want to do an example where we can actually nonetheless compute a solution by hand. And so this next example, I guess this will be example 2. This won't involve the error function. It'll just be like an honest like calculus computation. And so we're going to consider the initial value problem, again, where we have the solution to the diffusion equation. And suppose when, excuse me, at time 0, the function u is equal to e to the minus x. Right, so in this case, my function phi of x is just e to the minus x. Well, it's going to turn out, as I just said, that we can actually explicitly calculate in closed form what the solution u has to be, and so that's what we'll do now. And so my function u of xt, well, it has to equal 1 over square root of 4 pi kt, just using the solution formula. Excuse me. E to the minus x minus y squared over 4kt. And then, well, my function phi is e to the minus x, so I get e to the minus y dy here. And so what we're going to do is just do an algebraic trick to combine these two exponential terms into something that we can actually find the antiderivative of and integrate. And so, well, note that in the integrand, we have, we have e to, say, minus x minus y squared over 4kt, and then minus y. And so what we're going to do is this term in brackets, we just do some algebra to rewrite it in terms of something that we can integrate, right? And so let's expand this term. So the bracket term, well, what is it equal to? Well, I have minus, if I expand the square, I get x squared plus y squared minus 2xy over 4kt. And then this other term, well, I have a minus y, and if I want to bring it into the numerator here, I just have to multiply by 4kt, right? So it's equal to this. And so, well, the idea is, well, I want to write this as e to the minus something right, as e to the minus something squared. Because, well, let's say, I mean, the idea is to hope to write this as e to the minus something squared times something else, which we can, which is independent of the integration variable, right? So independent of y, for example, because, well, we know that if we integrate e to the minus something squared, we have this formula for the integral of the Gaussian, which we derived in the first homework set, which just tells us what the integral should be equal to. And then maybe we'll have this other term, which could depend on x and t, which we'll just factor out of the integral. And so we'll be able to arrive at a solution. And so that's the motivation for this calculation. And so what you want to do is write, basically complete the square for the bracket term. Right, and so what I'm going to do, I mean, you can read the calculation in the book. I don't want to just be taking up lecture time, just doing a bunch of algebra in front of you. So what I'm just going to write is just complete the square. Again, if you want to see the details, you can open up the textbook, or you can just pause the lecture, and maybe it would be a good exercise to review some algebra to just do this for yourself. And so you can write this now as minus y plus 2kt minus x all squared divided by 4kt. And then you have the sort of error term arising from completing the square, which is what's left over when you try to write the thing on the left as the square of something. And so that turns out to be kt minus x, right? And so if I now plug this into the integral, I get u of xt is equal to 1 over square root of 4 pi kt, integral from minus infinity to infinity. What am I left with? Well, I have, well, this was just this is what I was plugging into the exponential, right? This is what is in the brackets above. And so I end up with, well, I have minus y plus 2kt minus x squared over 4kt. And then I have this other term which doesn't depend on y at all. So I have plus kt minus x integrating with respect to y. And so the piece of the exponential that corresponds to these terms I can just factor out, right? So I can now write u of xt as, well, sorry, I just want to double check I don't get a minus sign wrong. Right, that's right. Okay. All right, so I get e to the kt minus x, which I'm just factoring out. And then I have what's left over, right? So 1 over square root 4 pi kt, integral from minus infinity to infinity of e to the minus y plus 2kt minus x squared over 4kt, integrating with respect to y. Right, and so this may look very complicated, but the idea here is, well, now I can notice that I'm integrating with respect to y from minus infinity to infinity. And in this parentheses and the term that's squared, I just have y shifted by some other number, which let me call this thing like, let's call this w, where w is 2kt minus x. Well, if I just change variables, say y plus w is equal to p, notice when I make this substitution, the bounds of the integral don't change because it's still from minus infinity to infinity, and p and y have the same sign, right? So you don't have to worry about that. And then if I do that, well, this is going to simplify dramatically, right? So then I end up with basically all these complicated 2kt minus x terms will just go away from the integral. So I end up with e to the kt minus x times 1 over square root 4 pi kt, integral minus infinity to infinity of e to the minus w squared over 4kt dw. Okay. And then finally, what I'm going to do is just, I want to make this look like the Gaussian, which we know the value of. So I'm just going to do one more substitution, which is the same substitution we did up here. And so what I'll finally do is, I guess this should be, right, so what I wrote down here in the integral is correct, but maybe it's confusing because I use W instead of P, but hopefully this is fine at this point. Right, and so what I'm finally going to do now is I want this to just look like the Gaussian integral that we know the value of, so I'm going to let W equal, sorry, I'm going to substitute in, well, I want to write this as e to the minus my variable squared, so the natural choice for the variable is W over the square root of 4kt. I'm going to let this be P. And if I make this substitution, then dP is 1 over square root of 4kt dW. Again, we have this term, this constant factor outside the integral will be absorbed when I make this change of variables. And so this ends up being e to the kt minus x times, well, I'm still left with 1 over square root of pi, integral from minus infinity to infinity of e to the minus p squared dp. And well, this is just the Gaussian that we know the value of, Gaussian integral from homework 1. Right. And so in particular, I think in homework 1, we had like p squared divided by 2. But if you just, I mean, you can do, if you just do another substitution, you can bring it into this form, and you can just check that this is equal to square root of pi, right? And so the square root of pi cancels out with the 1 over square root of pi, and so I just end up with this extra term, e to the kt minus x, and this is my solution, right? And so again, just reviewing, why could we actually calculate a solution? We could calculate a solution because my initial condition was an exponential function, and so I can do some algebraic manipulations to write the exponential into a form that I know how to integrate, right? So this is how the argument worked. The details are a little bit complicated, right? You have to remember how to complete the square. But it's, I mean, even though the details are complicated, it's worth seeing this calculation because this is a pretty common trick for calculating integrals, or not even calculating, just understanding integrals that involve Gaussian terms. Well, maybe you have some other factor, and what you try to do is write everything as a square of something, plus maybe some error terms, which you can hopefully factor out of the integral. And then doing some change of variables or some substitutions, you can just reduce matters to this Gaussian integral, which we know the value of, and then times the other terms, which could depend on p and x. Okay. And so I just want to comment a little bit further on this solution, and then we'll move on to the next section. Right, so the main point is, well, notice, let's look at this particular solution. Right, so e to the kt minus x. Well, remember that k is usually positive for us. And so what happens if I let t go to infinity? Well, I take limit as t goes to infinity of e to the kt minus x. This is infinite, right? It blows up, right? And so this would appear to contradict the maximum principle. Right, and so why does it appear to contradict the maximum principle? Well, this is my t-axis, right? So let's say this is when t is equal to some value t, capital T. Well, as I let this go to infinity, the value of my solution gets bigger and bigger, meaning the maximum value is going to keep growing, right? And so So the function just kind of blows up without any bound. And so, I mean, what this really tells you is, well, actually, let me rephrase this, right? So the point is that right, sorry, I just need I wasn't saying that the correct way, so let me just rephrase this. The point is, well, okay, we studied the maximum principle in the past few lectures last week and the week before this, and in all these cases we were looking at the maximum principle on a bounded domain, right? And here, well, we have a solution to the diffusion equation on unbounded domain. Right, and so what is the unbounded domain in this case? Well, we're on the real line, so x is between minus infinity and infinity, and t is just bigger than 0, meaning t is between 0 and infinity, right? And so in this case, we don't have like a rectangle as we did previously when we looked at the maximum principle. We have just the whole upper half plane in the xy plane, right? So this is our domain, it's just everything, right? And so in this domain, the boundary is just the x-axis, right? X is between minus infinity and infinity, right? And so you can ask yourself, well, is there an analog of the maximum principle for unbounded domains? And what this example shows is that the answer is no, right? So this example shows there is no maximum principle for unbounded domains. Right, and so why is this? Well, this is because, well, if I let t go to infinity, the solution blows up. Meaning it goes to infinity. So it gets larger and larger. Right? Meaning the maximum can't be attained on the boundary. So max is not on the boundary. Right, because for any particular boundary value you pick, I can always make my solution larger. Right? And so what's going on here? Well, why is there a failure of the maximum principle? Well, the idea is, well, let's go back to the initial condition, right? And so notice that, well, when I plug in t equals 0, my initial condition was e to the minus x, but for values of x which are approaching minus infinity, this gets arbitrarily large, right? And so the existence of an unbounded domain allows for initial conditions which are essentially like infinite heat sources, right? If you think about this in terms of heat flow, because, well, let's say I bring x out to like minus 1,000,000, well, then the initial state of U at this point is very large. And so as time increases, this corresponds to later in time, the solution getting like hotter and hotter or larger and larger. But I can make it, I don't have to stop there. I can just keep letting x have larger and larger absolute value while being negative, which makes the function U in the initial state larger and larger, which has the effect of making the solution to the diffusion equation get larger and larger. Right, and so this type of phenomenon, which can only happen if you have an unbounded domain, prevents there from being any kind of maximum principle. Right, so it turns out that in order to have maximum principle, you need a bounded domain. is the point. And this is an example that shows why. Okay, and so for the final part of the lecture today, I just want to discuss some comparisons between the wave and the diffusion equation. And then what we're going to do next time is start talking about the non-homogeneous versions of these equations, meaning we'll look at, for example, an equation where instead of having like a 0 on the right-hand side, we'll have some other function of x and t, right, for both the wave and diffusion equations. But before we do that, right, just to end the lecture today, I just want to make some brief comments about the comparison between the wave and diffusion equation. Right, and so there's a chart in the book which collects basically everything that I'm going to talk about now. I just want to maybe elaborate on some points a little bit differently or in a slightly different way than what's in the textbook. Right, and so what I'm going to do is just list out some properties and discuss how they, like, if they hold for the wave equation, if they hold for the diffusion equation, how they're different. And so the first thing, which turned out to be very important for our study of the wave equation, is the speed of propagation. Right, meaning basically the speed at which a solution moves, right? So if you think of the wave equation as a traveling wave, we saw that if you have this constant c, then the wave can only travel at speed c, right? So for the wave equation, which remember is utt minus c squared uxx is equal to 0. Diffusion equation is ut minus k times ux is equal to 0. Wave equation, we saw that it travels at finite speed, right? In particular, the speed is always less than or equal to c. And so this was a consequence of basically just looking at D'Alembert's formula. Right, we had this whole discussion on the causality phenomenon for the wave equation, which resulted from analyzing the D'Alembert formula. And we deduced from this that the solution can only move at speed c. For the diffusion equation, surprisingly, this fails dramatically. So for the diffusion equation, it's possible for the solution to travel at infinite speed. Right, and so what does it mean for something to travel at infinite speed? Well, this means, for example, maybe your initial condition is 0 outside of a small region, but immediately after a very short period of time, your solution U is non-zero everywhere, right? At every point going out to infinity on the unbounded domain. And so you have if you want to like understand this more precisely, you'll be able to do this in the homework for this week. So there's a homework problem for this week, which you should be working on now, which gives a precise example, or in this problem, you'll find a precise example which explains how the solution can kind of jump and move at basically infinite speed. And so, I mean, what does this mean? Does this mean that if you study diffusion phenomenon in physics, that particles are moving at infinite speed from one point to another? No, it doesn't necessarily mean that. It just means that there's potentially a flaw in the model, and the model is not 100% accurate. That's one perspective to take away from this, right? Okay, and so, right, the second thing I want to talk about relating the wave and diffusion equations. Well, the first property here was related to causality, which was one of the defining features of the wave equation. What's the first thing we looked at for the diffusion equation? This was the maximum principle. For the wave equation, you can ask, Well, does the wave equation have some kind of version of the maximum principle? The answer is no, even on bounded domains. So it turns out that the maximum principle is a kind of an important feature of the diffusion equation and not the wave equation. And so this will be on your next homework. You'll have a problem where you study this in more detail. It's not too hard. You can understand this just by looking at simple initial conditions. And so I'll give you an example which you can work through on your homework, which will explain why there's no maximum principle for the wave equation. For the diffusion equation, of course, there is unbounded domains. But what we saw in this previous example was that if you relax this assumption and you allow your domain to be unbounded, well, then your initial conditions can blow up in either the left or the right direction, which corresponds to your solution like growing rapidly with time. And so there can't be a maximum principle because the maximum value is out at infinity. Okay, great. And so, right, so the next property I wanted to discuss as it relates to the diffusion wave equation is the behavior as t goes to infinity. Well, what happens to the wave equation as time goes to infinity? It basically transports data to left or right at speed c. I mean, there could be some other interaction, but does not decay in general. I mean, sure, you could have like some traveling waves which are interfering with one another in complicated waves, and maybe the amplitude decreases at certain points. But you can write down solutions to the wave equation where it's just transporting the wave to the left or the right, and nothing is decaying, right? So as time increases, there's no decay in the solution. On the other hand, for the diffusion equation, well, if your initial condition is integrable, in the sense that if I integrate absolute value of phi, that this is finite on the whole real line, then the solution has to decay as t goes to infinity, right? And so what do I mean by this? Let me just do this precisely. So let me prove this point here. Well, my solution u of xt is given by this term involving t, integral from minus infinity to infinity of this Gaussian, and then phi of y. And what I want to show is, well, if my initial condition is integrable, then the solution has to decay as t goes to infinity. Well, what I'm going to do is just use a common integral estimate, which is, well, if I take the absolute value of u of xt, this is just the absolute value of the integral. Right? And well, if you take absolute value of the integral of some function, this is always less than or equal to the integral of the absolute value, right? Because what is the integral is measuring not just the area under the curve, but the signed area, right? And so in regions where you have negative area, it's canceling out a little bit. But if you just integrate the absolute value, there's no negative region, right? And so it's always going to be bigger. It's a basic reason why this is true. And so if I use this inequality, well, then this is always less than or equal to, well, everything is positive except possibly the initial condition phi. And so I'm left with 1 over square root 4k t pi. integral from minus infinity to infinity, e to the minus x minus y squared over 4kt, and then absolute value of phi of y dy. But this exponential term is always less than or equal to 1, right? It doesn't matter how complicated the formula is, since it's negative, e to whatever this thing is always smaller than 1. And so this tells me that u of xt is always less than or equal to 1 over square root of 4k t pi times integral from minus infinity to infinity of absolute value of phi of y dy. And we're assuming, right up here, we were assuming that this quantity was finite. And so this is just some number. And so this is of the form, well, I have 1 over square root of t, and then I have some constant which depends on phi, right? So some constant depending on phi, but it's independent of t. Right? And so if I take the limit as t goes to infinity, well, I have t to a negative power times a constant, and so this thing goes to 0, right? And so by the squeeze theorem, the solution decays, right? And so this implies again that if your initial condition is integrable, meaning the integral from minus infinity to infinity of its absolute value is finite, then the solution to the diffusion equation has to decay as t goes to infinity. On the other hand, for the wave equation, that's certainly not the case, because you could just have a traveling wave which moves to the right at speed c for all time and never decays or anything like that. It just moves around. Okay, and so that's, I guess those are the three main points I wanted to talk about in a little bit more detail, which distinguish the behavior of the wave and diffusion equation. Maybe one more final point about this argument. We'll notice that in the last example where we actually calculated a solution, this property failed, right? So the limit as t goes to infinity of this function u of xt was infinite, right? Well, so I thought we just proved that it should be 0, not infinity, right? Well, where does this argument fail? This argument fails because the initial condition is not integrable here, right? So for this function, your initial condition is phi of x. If I look at integral of absolute value of phi to the x, or sorry, of phi of x, this is not finite, right? The issue is that if, of course, if x is positive, then it decays and it's integrable. The issue is if x is negative, you're integrating e to the absolute value of x, which blows up, right? So this is certainly not a finite integral, right? And so while this shows that if you remove the assumption about the initial data being integrable, then maybe the solution doesn't decay. And this is an example where it doesn't decay. But if your initial condition is integrable, then the solution does have to decay. Okay, and so that's about it. And so then, as I mentioned before, in the next lecture, we'll talk about the non-homogeneous versions of these equations.